Good afternoon, ladies and gentlemen. I will show you in the next few minutes some latest developments that have been done in-house in SERVA on the area of mini-gel electrophoresis. And these new developments contain a chamber, special chamber. You see that already on the screen. And I will explain more to this in the end. But the major development is the buffer systems in the gels. Before I introduce the gels to you, I just suggest that we take a small walk through the basics of electrophoresis, of protein electrophoresis particularly. And the first thing what you see here is the very simple principle of electrophoresis, the migration of charged particles, molecules in an electric field. You see on the right in the animation that when you have different particles, they are migrating with different velocities. On the left-hand side, you see a particle negatively charged migrating in the electric field towards the anode. And there is a very simplified equation here. It's not an official, it's very simplified, which tells you the velocity of the particle is equal to the electrophoretic mobility, which is a rather complex thing, times the electric field strength. Electric field strength is measured in volts per centimeter, so the higher the voltage you apply on a certain gel, the faster the particles will migrate. And depending on the mobilities, they will migrate faster or slower, and the result is a migration electric field and different zones. Here you see what most of the people do when they perform protein electrophoresis. They apply SDS Disc electrophoresis, which has been introduced in the year 1970 by Professor Lemley from Switzerland. On the right you see an animation how the discontinuous buffer system works. On the left you see the different phases of the disc electrophoresis. So here you see a resolving gel, and usually in the most applied disc electrophoresis systems you have a tris chloride gel containing gel with pH 8.8, and on top of the narrow pore size resolving gel you have large pore size stacking gel with a tris chloride buffer 6.8, and then you apply the sample, and the upper running buffer contains a different ion, not chloride but glycine, a slow migration ion. In the anode side, you can also use tris chloride. So, of course, most of the people are using tris glycine. It doesn't matter, but you can also save the glycine for the anode. What is important is what happens here in this area. When you apply the electric field, the anions, the glycine, the proteins, and the chloride start to migrate towards the anode. And there is an effect which is called the stacking effect, that you get sharpening of the zones. Then when the proteins arrive at the narrow pore size resolving gel, they will be slowed down, and you see that very nicely on the animation right. Now the glycine is taking over, is passing through the proteins, and suddenly the pH of the system will rise to pH 9.5, and you get usually a very sharp and very good resolution separation in that system, disc electrophoresis system. A few words for sample preparation when you perform SDS electrophoresis. So SDS is a very efficient anionic detergent, and when you apply it on the proteins sample, the charges, the own charges of the polypeptides will be covered with negative charges, so all molecules will migrate into the same direction towards the anode. This is a denaturating effect. You have different ways how to run SDS electrophoresis. You can use a non-reducing treatment, then you do not have a complete unfolding of the molecules. Then you cannot easily draw a conclusion to the size of the molecules. Usually the people are using a reducting reagent, DTT, DTE, or beta-mercaptoethanol. Then you lose the quaternary structures and you see only the subunits, but you get a complete unfolding of the molecules and better sieving, more efficient sieving, and you can relate the migration to the size of the molecules, to the length of the polypeptide chain. Now this reduction, and I show you that we recommend to do that at 60 degrees. So in the previous webinar, somebody has asked why not 99 degrees, but 60 degrees is safer to avoid fragmentations of some of the proteins. Some of the proteins are sensitive to fragmentation. We know that meanwhile, so we recommend usually 60 degrees for the SDS treatment, but for a longer time, 5 minutes to 10 minutes. In order to avoid back foldings and other artifacts, usually people are using an alkylation step afterwards with iodoacetamide or vinylpyridine, and then you have a more stable form of the molecules. So I just want to sum up why so many people are performing SDS electrophoresis when they separate proteins. First of all, this anionic detergent gives us a very efficient solubilization. We want to get all proteins in solution, and here with SDS we have a very good chance for that. Secondly, all molecules will migrate into the same direction. That's not the case in native electrophoresis, and because you have the different charges, and here the individual charges are covered by the detergent, by the SDS. You can assess molecular weights, better to say molecular sizes. The separation is quicker than native because you have a higher charge density on the molecules, and so they migrate faster. You get a very high resolution and sharp zones because of the unfolding of the molecules, so more efficient sieving in the gel, retardation in the gel. Also, this is the reason for a very easy fixation. You will see one band for one enzyme because the individual conformations are cancelled, and so you in isoelectric focusing or native electrophoresis, it can easily happen that you see more than one band for one enzyme. And you get an increased sensitivity for detection. Immunodetection for immunoblotting, it is a big advantage when the proteins are denatured with SDS because you have access for the antibodies to dock to the epitopes. However, polyacrylamide gel electrophoresis is not so easy. There are some things which you should bear in mind. First of all, when you make your own gels, the acrylamide monomers are toxic, and I can only warn to work with acrylamide monomers, you have to be very careful that you don't spill them on the bench and things like this. So we know about labs which have completely forbidden to work with monomers like acrylamide and also the cross-linker, the BIS. The ammonium persulfate is also very aggressive reagent, and so you have to be very careful with this as well. What you see here is that the polymerization effectiveness is dependent on a lot of parameters. The temperature, the higher the temperature, the more efficient the polymerization. Acrylamide concentration, higher, better. pH value, the optimum pH value for polymerization would be about neutral, about pH 7, which is not always the case, as you know. Oxygen, you should exclude oxygen, leads to chain breaking of the chains, stopping of the chain production. And there are sometimes inhibitors in the additives, and the quality of reagents play an important role. So it's a quite complex thing. Still, when the gels have been polymerized, they are, depending on the effectiveness of the polymerized, more or less monomers, which can create troubles with some of the proteins. Ammonium persulfate can also react with some proteins, so be careful. Another problem is that when you need a high pH value in the gel, like in the classical Lemley gel buffer which I have just introduced, the pH is rather high, and that can lead to alkaline hydrolysis with the time, so the gels are not very stable with the time. So therefore, classical tris glycine gels must be stored in a refrigerator and used within 6 to 8 weeks due to the alkaline hydrolysis of the polyacrylamide matrix at pH 8.8. So what can you do to have gels which have a longer shelf life? For instance, ready-made gels need a longer shelf life than only a few weeks. So some of the producers of gels have found a trick to use alternative buffers which establish a pH below 7 so that the gels have a longer shelf life. But these amphoteric buffers, which are used very often in this case, lead to modified separation, to modified separation parameters. Many people want to have the separation parameters of a typical classical tris glycine gel, and that was so far not possible to make ready-made gels for this particular buffer system. So I now introduce to you our series of the SERVA gel TG prime. TG means tris glycine, and prime, I forgot to say that already in the beginning, is just a short name, an abbreviation of premium resolution in mini-gel electrophoresis, just a name which is easier to remember. And we needed a new name for it because it's a new system, has not been existing so far. The gels contain tris, chloride, glycine, water, and acrylamide, nothing else. So the entire system is not working with additional amphoteric compounds. So these gels are modified Lemley gels. They have a long-term stability because their pH value in the gels is below 7. But during the separation, the pH jumps up to pH 9.5, which is important to get the separation according to the sieving of the gels. You might have seen in some websites that people say, yes, pH 9.5 is too high for protein separation, you can damage proteins. This all is not really true. We know that the pH 9.5 is important to get exactly the separation that you need for appropriate SDS electrophoresis. The gels themselves, however, do not contain SDS. So you can also use them for native polyacrylamide gel electrophoresis and also for DNA analysis. You just decide by selecting the appropriate running buffer and the sample preparation, what type of separation you will perform. The separation parameters are just exactly like the lab cast gels because they are indeed Lemley gels. They are also run with Lemley electrophoresis buffer, and they are polymerized at a very optimum pH. It's about pH 7, as I said before, so you do not have toxic monomers anymore. You have a very efficient polymerization in these gels, much better than in homemade gels. Here you see now a comparison between a typical tris chloride pH 8.8. This is a this is a gradient 4 to 20 T, and the left is just what you cast in a lab with a pH 8.8. And when we modify our buffer system for making the gels longer stable, we have a second very positive effect. We get sharper zones, particularly in the low molecular weight area, as you see, for instance, here. About the sealing properties of SDS gels. Maybe you have seen this curve. This is the relation between the logarithms of the molecular sizes, it's more correct than molecular weights, and the relative mobility after SDS electrophoresis. The relative mobility is usually measured with the front marker with a bromophenol blue, and you get a sigmoidal curve. The linear part of the sigmoidal curve is depending on the gel concentration. So if you have a higher concentrated gel, it's further down. If you have a lower concentrated gel, it's further up. And for a porosity gradient gel, you have a wider linear range. And another hint here, 1.4 gram SDS you need about to cover 1 gram protein completely to achieve this performance. Here I show you some selectivity curves for our homogeneous gels as well as for the gradient gels. Here you see the gels that we offer, the 8, 10, 12, and 14 homogeneous and the different gradient gels, and you see that the homogeneous gels have a very steep, very high selectivity of molecular size separation, whereas gradient gels have a much wider range of separation, but the resolution in the areas are more distributed, more evenly distributed. Here you see now some real results of these gels, 8, 10, 12, and 14 homogeneous gels with the same samples, and you see the typical dependence on the migration on the gel concentration. This is for homogeneous gels, and here you see the same for gradient gels, but here the differences are not so dramatic like for homogeneous gels, as you see. Here is our gradient 4 to 20, and with the marker proteins you see that we have a very wide separation range, and what is, I would say, spectacular, we reach down to 3, even a little bit lower than 3 kilodalton, which is very unique for glycine gels. Usually you have the limit at about 10 kilodaltons and you won't see the smaller bands anymore. That's very special for our buffer system, and that was just coming with the development. Now, there is another interesting thing. You can combine these gels with different, with different running buffers. So these are the ones we have in our program. For instance, tris-glycine, which is the classical. We have tris-trizine. There's the maize is missing here, but also the MOPS buffer. And you can also use a non-SDS buffer like tris-glycine for native separations, and for separating DNA fragments, you can use the tris-borate EDTA buffer system. And I will show you some examples in the next slides. So here, there was the same gels, not the identical of course, but the same gel, the prime gel 4 to 12, run with the same samples basically, but with different running buffers. Here the tris-glycine SDS, here the tris-trizine SDS, here the tris-MOPS SDS, and here the tris-maize SDS. And you will see that particularly the MOPS and the maize shows you an even better resolution in the low molecular weight area. And we get quite fast separation time. So a separation like this takes about 35 to 40 minutes. This is quite fast. This is markedly faster than homemade gels and much faster than typical peptide gels. These gels are also available in a 2D version. There are 3 of them selected, I always say pH, a porosity gradient from 8 to 16%, but also two homogeneous gels, one with 12 and another one with 14% T for high resolution 2D electrophoresis. Here you see now a native separation. Here the buffer without the SDS was used as a running buffer, and here you see also there is a longer separation time, 2 hours 10 minutes for the same gel, which in an SDS version runs about in 40 minutes. But this is because native proteins are not so highly charged like SDS proteins. And here is an example. Of course, we are talking about protein electrophoresis today, but I don't want to miss the chance to show you that also DNA fragments can be successfully separated in such gels and just using the TBE running buffer instead of, for instance, crystallizing buffer. The last thing I want to show you is our development of the instrument. And this is our blue vertical prime electrophoresis unit, which can run 2 gels at a time, but you can also run 1 gel at a time if you use a dummy plate on the one side. And this is a construction which is completely without clamps or without screws. Very easy to use. You just open it up, put the cassette inside, and then you hook it up like this. It's very easy to assemble and disassemble, and not parts around. It's very easy to use and is only available from us. Saying that, I want to mention also that these gels can of course also be run in other chambers than our blue verticals. There are chambers around in some labs which can also hold these cassettes. If you want to know which ones, you can send us a question in the email answer, in the email reply, of course they don't fit into every chambers, because some companies make chambers which are a little bit larger or which are a little bit smaller, but there are quite a few which can also run these gels. I think that's all what I wanted to tell you, of course, and now you can ask your questions and I'll try to answer them.